Thank you very much. Welcome everyone. My name is Britta, and today I'm giving you some insights on our paper, Incentives, Cooperation in Teams, Sociality Meets Decision Rights, and this is joint work with Pablo Alvarez and Christina Hadring. So what are we looking at here? On the one side, we are looking on enhancing cooperation in teams. Research has for decades now searched for incentives to increase cooperation in team settings, and also in corporations. This is always an important issue to have high cooperation levels in teamwork. Within our experiment, we capture cooperation using a public good game. Then we have an additional component, which is a social component on giving charitable donations. And these are directly tied to the cooperation level. This means the higher the cooperation is within the team, the higher are also the donation amounts that are generated. And if we maybe look in a company, you see that many companies do give to charities, and that maybe they could use this charitable giving also as strategical tool to increase cooperation in teams. So we have this main setting here, and now we are looking on decision rights. So if groups could decide of including such a donation incentive, if this would increase cooperation just by giving them the right to decide. So our research question is, does endogenous decision making about including a donation share into a public good game influence cooperation levels within the game? When we are looking at the existing literature, we have the literature on delegation of decision rights, and they mostly argue about that people want to be self-determined and they want to have autonomy about what they are doing. And we also see empirical findings that show that decision right itself might have intrinsic value for individuals. And we see, for example, in principal agent settings that people might increase effort levels when they just hold a decision right, for example, about their wage. Then we have the social incentives, and it seems to be important for individuals that they work for a mission, for example, and maybe also that their mission matches between maybe an agent and principal. And we also see in recent studies that it might be important to self-select in a social environment. So if we have such an environment which includes a social incentive, it might be especially important that they self-select into this setting to increase effort levels and cooperation. And then we have also already existing empirical studies that show that such a social incentive might work, and that it does increase cooperation levels within teams. And also in principal agent settings, we see if, for example, the principal decides to give to a charity, that the agents react to these altruistic preferences and might also increase effort levels towards the principal. When we now combine these two components, so we have the delegation of decision rights on social incentives, we have social preferences of altruism and warm glow that seem to be important, especially the warm glow that the act of giving actually gives you a good feeling, and when you have the decision right, this might even be stronger. And maybe you also have to pay, for example, for a donation, and that might also increase this warm and good feeling that you do something positive. And there's already existing literature from Tonen and Vlasopoulos. They included a donation incentive in real effort experiment on an individual level. So the higher the effort was, the more was also being donated. And they had also one treatment included where participants had the choice between including such an incentive or not. And they also find that the decision right itself does increase the effort levels here. And in contrast to the existing literature now, we are looking on a group setting where we try to increase the cooperation with giving this decision right about including a social incentive into the payout function. So we had 4 treatments. So in the main game, we played a repeated public good game over 10 rounds. We had groups of 4 people in a partner matching, and we have an MPCR of 0.5. So everything that goes to the group account is doubled. You see here in the baseline treatment, participants received 20 token in the beginning and could decide how much they keep for themselves and how much would go into the group account. And then this amount was doubled in the group account and then split again to the 4 people. In the baseline, participants did not have any decision right, and there was no donation included at all. Then we have the baseline donation. Again, we have no decision right, but this time we exogenously set a 20% donation share. So that was mandatory, and this 20% donation was subtracted from the group's payoff. So they actually, they pay by their money with their tokens for the charitable donation. And the 20% was also what went to the charity. So we had the group contributions, and that was doubled, and 20% of that was going to be donated. Then we have 2 treatments that include a decision right. The vote treatment, their participants could either vote in favor of including the 20% donation share or of not including a donation share at all. And this was a majority vote. And if a tie occurred, we had like a virtual coin toss that decided which if it was included or not. And participants in the groups were not aware what the other individuals had chosen. They just received information about the outcome of the vote here. And again, so if they voted in favor of no donation, they had the same payoff function than the baseline group. And if they voted in favor of the 20% donation, it was the same payoff function that the baseline donation. So we have a nice comparison here, which only differs in the decision right. Then we also made the vote share treatment. Here we gave kind of a bit more autonomy to the participants. So this time they could decide on a donation share between 0 and 20. And then the average of the 4 group members was the share that was implemented in the public good. And again, that was subtracted from the group account. And that was also the amount that was going to be donated to the charity. What did we predict here? Out of the reasons of self-determination, autonomy, and the existing results in literature on empirical studies, we predicted that the vote and vote share treatment have higher cooperation levels compared to the other ones. And we also thought, because of a higher degree of autonomy in the vote share treatment, that the cooperation might even be stronger in this treatment compared to the vote treatment. But we also have to consider that there might be negative effects. For example, if I would vote in favor of including 20% in the public good game, and then the outcome of the vote is that it is not implemented, I would have maybe a bad feeling and maybe wouldn't be happy to cooperate with the group at that stage. Then some general information about our experiments. So we had 12 sessions with an average duration of 90 minutes, 328 participants, mostly students, quite balanced in gender, and the average age was 24. Average payoffs were 40.3 euro, and we had over 600 euros of donation that we generated in the experiment. So how did it look like? So how was the concrete procedure? We gave a short introduction in the beginning. Then in all treatments, also in the baseline treatment, we explained that there might be possible donation payments and that they are able to observe these donation payments in the end of the experiment. Then we explained the public good game, and in the vote treatments, we explained how the decision procedure would work. And then we had some control questions to make sure participants understood how the game worked, and especially in the vote treatment, that they understood what their decision would change in the game and for their payoffs. And then we asked them for preferences for charitable organizations, so they could choose 1 out of 5 charities here. And this was an individual decision. Meaning that they were not informed about the other group members' decision on the charity, and also that they were just sure that 1/4 of the donation amount would go to their own favorite charity, and they did not know where the other fractions would go. Then in the vote treatment, the decision procedure followed, so they could state in favor or against the donation, or they could state the share of the donation that they would like to be implemented. And then we asked also about the belief about the other group members' decision about the vote. And after that, they were just informed how the result of the vote was. And then they knew that this was the payoff function and the setting which would they play until the end of the game. Then we conducted or followed the procedure of Fischbacher et al. So we had a one-shot contribution to a public good to capture the general willingness to pay. And then we also had the conditional contributions in regards to the average contributions of the other group members. And then the actual main public good game started here over 10 rounds. After the first round, we asked for the beliefs about the other group members' contributions. And after each round, we gave feedback on the average contributions of the other 3 group members and on the donation amounts that were generated in the experiment. And in the end, we wanted to capture some spillover effects. So we showed participants the total earnings from the experiment and asked if they would like to give a voluntary donation from that. And then followed a questionnaire about demographics, social preferences, for example, of altruism, trust and risk. And then we had some feedback questions to capture some more insight on how participants made the decision during the experiment. So maybe before I continue on going to the results, I would like to check if there are any questions, especially regarding the design at that point. Okay, I think there are no questions, otherwise just interrupt me. Okay, so again, what were we looking at? Does endogenous decision making about including a donation share into a public good game influence cooperation levels within the game? And in the following, we have a look on the 2 decision mechanisms separately. So first we look on the vote treatment. So participants could either state in favor or against the donation payment. 42% of the participants actually decided in favor of implementing the donation share of 20%. And in the end, in 46% of the groups, the donation share was really implemented. In this graph, you see that we split the vote treatment into those groups that did not implement the donation share, that is vote 0, and the groups that implemented the donation share, that is vote 20. And as a reminder, so baseline, no donation at all, and the baseline donation mandatorily set 20% donation here. Most obvious is here in the graph of the average contributions over rounds that in the vote 20 group, they are the highest contributions, especially in the second half of the experiment. When we look at non-parametric statistics, there are no significant differences over all rounds between the treatment variations. But what we see in the last round is that the vote 20 group has significantly higher contribution levels compared to the baseline where the donation was mandatorily set. When we look on the regression results, to point out here, this is the regression just for the second half of the experiment, so round 6 to 10. When we look over all rounds, we do not find significant differences, but when we more focus on stabilizing contributions, we see here that the vote 20 group does have significantly higher contribution levels compared to the baseline donation, where we exogenously implemented the 20% donation, so that the decision right itself does influence cooperation levels significantly here. And then we see typical patterns that the average group members' contributions from the previous round, conditional cooperators or the beliefs, have a significantly positive effect, and that over rounds the contribution levels do decrease here. When we then hop to the vote share treatment, first, how did the participants made their decision here? You see on the left-hand side the individual choice of each participant. You see that many people actually did vote in favor of implementing a donation share. You see some peaks at the 5 and 10% level here. And then on the right-hand side, you see the implemented donation share. So that was the average of all 4 group members. And these range from 1% to 11%. And so, to point out here, this is much lower than the 20% that we exogenously set. So when we compare later the different graphs, we might have to keep that in our mind, that there's still lower donation shares here compared to the mandatorily set donation share. And then when we have a first insight on the mean contributions, on the left-hand side, again, you see the individual donation share, which participants stated. And you see, a pattern that the higher the individual donation share is, the higher it's also the mean contribution. And also on the right-hand side, you see a pattern that the higher the implemented donation share is, the higher is also the group's average contribution.
5 minutes.
Yeah. Yes, thank you. And when we have a look on the graph here of the average contributions, again, we split the vote share treatment here, but this time we did a median split. So the vote share low group, there are donation shares of lower than 5.4%. And in the vote share high, the donation shares are higher than 5.4%. It looks a bit, more homogeneously compared to the vote treatment. People were not forced here to go for the extreme shares. That might be one reason. And when we look for the differences on non-parametric statistics, so there are no differences between treatment variations as a whole. But when we look for the last 5 rounds, we see that in the vote share high group, we have significantly higher contributions compared to the baseline donation. And also in the last round, we have significantly higher contributions in the vote share treatment as a whole, and also in vote share high and the vote share low group compared to the baseline donation, where we have this mandatorily set 20% donation share. When we look on the results here for the regression, again, this is just the last 5 rounds, we see similar patterns. Like in the vote treatment, for the vote share high dummy, we see significantly higher contributions in the first 3 models. So this does not hold for the last model when we include all control variables, but the other patterns are similar or the same compared to the vote treatment. And now wrapping up our key findings. So first of all, a large percentage of participants voted in favor of implementing a donation share, which we find quite interesting, as it seems that people are really interested in such incentive systems. Then we see that the decision right stabilizes contribution levels over rounds, as we see that the vote and vote share treatment has significantly higher contributions in the last round compared to the groups where we have this mandatorily set 20% donation share. And we see that groups that actually implement the 20% donation by vote and groups that implement a high donation share in the vote share treatments contribute significantly more in the second half of the game and also stabilize the contribution levels here compared to groups where we exogenously implemented the donation share. We also had a look on the deviation between the individual vote and the implemented donation. As I said, there might also be negative effects, and that's what we also see, that people might not be satisfied with the outcome of the implemented donation, or if the share, the deviation is very high in the vote share treatment, that they might reduce their cooperation during the experiment. Then we also had a look on different types of players in the game. There we couldn't do any testing because the sample sizes get very small here. But we see, for example, people who vote in favor of 20% and then they start with high contributions and they keep that level over the whole experiment. So that might be more the altruistic type of people. And also we have participants that maybe state, vote against the donation payment, but they still start with high contributions, maybe to enhance cooperation in the beginning, and then they decrease contributions over rounds to maybe profit from the others. That might more be strategical players who try to maximize their own profit. And then when we go more to the practical sides, a company, for example, they might need to make the trade-off between the increased cooperation that they have when delegating the decision right, but also reduce donation payments. For example, in the vote treatment, we saw that contributions rise by 17%, but that we also have a total reduction of 40% of the donation payments. And the donation payments might also have value for the firm, as they might use this for for their marketing or things like this. So this is really what, later in a company, people would need to make the trade-off for. And then what's also interesting is when we shift from the baseline donation, so not including a donation share at all, to the vote treatments where we delegate the decision right, we do not find any significant differences. So it seems that companies might be able to generate costless donation payments with endogenous decision making in this case. But for sure, to transfer this to a real setting, we need more investigation in these kind of incentives. All right, then so far I would like to thank you for your attention, and I'm happy for any feedback or questions now.
Thank you. This is the time for questions. So if there are no questions, maybe I will ask one if possible. So basically your results goes against licensing. I understand it correctly?
It goes against licensing.
I mean yeah.
So licensing wouldn't mean, but wouldn't that mean that when they would be pro-social in the beginning, they reduce their pro-social activities afterwards?
Yeah, kind of. I voted to donate, so I did my part. So now I can stop here.
So that was actually something that we tried to have a look on with the spillover effects. So I didn't show any of these results, so we didn't find real evidence in our data, because like we had the social environment in our experiment in the public good game, and then we wanted to see with the spillover effects if people, if they already be so social in the experiment, they would reduce their sociality in the donation payments at the end, in the voluntary donation payments, but we did not find any patterns for that. But within the game, I cannot see the connection at the moment for the licensing. Can you explain it?
Can I explain it? I don't know.
So within the game, I think this is just, or do you mean if they vote in favor of the donation payment in the beginning, so they show that they're social, and then they would not cooperate because they were already social in voting in favor of the donation?
This is what the licensing theory predicts. I'm not one of the big fans of the licensing theory, but I just say what it predicts.
Yeah. I haven't concretely had a look at that, but that is a good point. So we could have, we could check if the decision in the beginning, we would have some licensing of the, in comparison of the decision and the cooperation levels within the game. Yeah. Thank you. All right. Yeah, I'm also happy to receive any emails or if you have any comments or questions afterwards. So that's fine as well. So we might, we can stick to the schedule now then, I think.
Yeah, so if you have something to add, you have, I think, 1 or 2 more minutes, so you can add something.
So yeah, maybe I can, what we also looked at, maybe that's also interesting to see, as we had the majority and not majority votes, for example. So we had groups in which a tie occurred and groups in which not, which was really by majority. But here we have to be very careful because the vote 0 tie, so where we have not included a donation share, after a tie, these were just, I think, 4 groups. So, but this might be first indications also that we, like the more, heterogeneous the group is, the harder it is to cooperate for these groups. And if you go for majority vote, the more happy the people are. So that's maybe just a short key finding for the end. But further investigation would need to be done here as well.
Okay, Britta, thank you so much.
Thank you too.
So
thanks for joining.
The next speaker should be Sergio Alessandro. and I'm not sure that he's here. Am I correct? So Sergio, if you are
I
here.
also don't see him among participants.
Yeah. So unless you have other suggestions, sorry?
Probably we move to the next presenter.
I suggest that we just take a break so that we stick to the schedule, but if, Ori, what do you think?
Yeah, I'm not sure how to play this, but I'm okay with taking a break now until
Whatever you
10 to
prefer.
12.
Like, I'm fine with.
Because it also depends on you, because you'll be the last speaker. So voting against the break. Okay, so there's people in the crowd are have opinions. Okay, so I'll just
so let's
go ahead
continue
and
for
start.
now. Yeah.
Yeah, I'll just go ahead and start.
Okay.
Okay.
All the lectures will be recorded, so the people
that the organizer asks that they will take a break. Of course, if we're gonna miss some of the participants, that will be sad.
Okay, so now, yeah, so now also we have another member of the crowd voting against
I think they were explicit.
forced ticket schedule. Yeah.
So okay, so let's take a break, and we will continue in about. Let me make the calculation in 20 minutes, right?
So yeah, 20 minutes.
Okay, so you can stay here, just mute yourself, and we will continue, or you can go to, or whatever, and we will be back in 20 minutes. Okay, I think if you're ready, you can start.
Okay, sure. So hi everyone, thanks for coming back. This is joint work with Yefim that you'll hear from later as well. And this is titled When Both Players Choose Dominated Strategies, Underweighting of Rare Events in Two-Person Repeated Games. And although this session is about repeated games and this talk will be about repeated games, I want to start actually with a brief introduction in the context of individual decisions. And in individual decisions, we have, of course, perhaps the most prominent theory of choice in behavioral economics, which is prospect theory, dealing with what we frame as decisions from description, which is a choice between pairs of gambles. And this is one example for such choice. So you can ask people, please choose between 6.8 with certainty or 7.3 with probability 0.96 minus 8.5 otherwise, so with probability 0.04. And in this case, prospect theory and its derivatives teach us that people tend to behave as if they overweight the rare events. So it is as if the rare event, which in this case is a bad loss, 8.5, gets more weight than it truly deserves, which is 4% here. And in this case, Heltwig and Adolf actually ran this experiment, and they found, one point is that this prospect has a expected value of 6.7. So it's very similar to the other prospect in terms of expected value. And Heltwig and Adolf actually ran this experiment, and they found that only 16% choose this gamble, this risky gamble, and most people prefer the safer option here. So this is consistent with a few explanations, including risk aversion, but it is also consistent with the idea that people tend to overweight the rare event. So if they think that the rare 8.5 loss will happen in more than 4% of the time, then it's justified to select the gamble only rarely. And lately, in the last 2 decades actually, so this is overrating of reference. In the last 2 decades actually, there is a whole literature on what we call decisions from experience. Decisions from experience are decisions that in which one example for a paradigm that tests this is this one. People see 2 buttons on a screen, please click on a button, that's all they say, that's all they know. And then let's say that they click on the left one. Sorry. Let's say that they click on the left one, right? So they get 6.8, and they see that they could have gotten 7.3 had they clicked on the other one. And let's say now that they click on the right one, they get 7.3. They could have gotten 6.8 had they clicked on the other one, and so on and so forth. And this happens many times, many rounds. And here, people have to learn the prospects from experience, from the feedback that they get. And in fact, Hedwig and I have actually ran this report, running this study, where the same exact prospects from the left, from the decision from description, were played from experience using this paradigm. And here, what they see is that people choose the risky gamble 59% of the time. So here, people prefer the gamble, the risky gamble, despite of risk aversion, despite of it containing losses, despite of the fact that it has a slightly lower expected value, when they choose from experience, they select this gamble more often than not. And this is behavior that is consistent with the exact opposite of the overweighting of rare events that we know from prospect theory and derivatives, which is underweighting of rare events. And we know that there's a description experience gap in this kind of decisions. So whether people play a phase decision from description or from experience matters in relation to their behavior when rare events are present. Now, this underweighting of rare events has been reported in decisions with feedback across many different paradigms, and this is a short list, including repeated decision with partial or biased feedback. It doesn't have to be a repeated decision, so it could be one-shot decisions, but when people get experience using sampling of the two options, it could be two-stage sequential decisions. It could be outside the context of risky gambles, investment decisions, time-saving decisions, consumer choice. Even bees behave as if they underweight rare events. And the last two are important. It also happens to be true when people get both experience and description. So it seems like the effect of experience, the underweighting of rare events that happens from experience, trumps those of description. So people underweight rare events when they get repeated, when they have to choose repeatedly between decisions from description. So the same decision over and over again, they get feedback each time. And surprisingly, they also do this when they get, when they repeatedly choose between decision from description. Each one is completely different than the other, although they are highly similar and all including some types of rare events. Then when people get feedback on previous choices, they also behave as if they underweight rare events. Now, although this has been shown in many different contexts with feedback, this hasn't been shown, as far as we know, in games. So this is what we set out to do. And here, it makes sense to test because there's a whole new, set of behaviors that could go in and change this pattern of underweighting of rare events. The fact that people interact with another person may trigger, for example, other regarding preferences, efficiency, fairness, reciprocity, all sorts of these things that you know very well. And so it might be this pattern that we see in individual decisions, this bias that we see in individual decisions will not emerge in games. And it is very important to look at this in games because almost every decision that in the real world that we can, that I can think of involves both social uncertainty and environmental uncertainty. Social uncertainty being the fact that what I do affects others and what others do affect me, and environmental uncertainty being the fact that regardless of what we all do, it's not determined that the outcomes will be fixed. So it could be some sort of risk involved. So almost everything you do, including, for example, our decisions during coronavirus times, whether to wear a mask and so on. It involves both social and environmental uncertainty. So when I decide whether I should wear a mask in this location, I may affect others, others' choice may affect me, and of course, it could be that we all don't wear masks and no one gets infected, so there is environmental uncertainty as well. Now, another reason to investigate this is that when a player underweights rare events, if that is indeed the case, the players underweight rare events in games as well, how do the other players respond to this bias? Could they exploit it? This, we don't know. This is something we need to test. So we set out to test this in an experiment. And before I show you what we actually ran, I want to show you this benign game, just to walk you through how we did it in practice. But this game is a two-person game. Player one chooses between in or out. Out is the outside option, gives player one 0 with certainty, and will ensure a loss of 5 for player two. Player two, if she gets to play, well, she decides in any case, whether she plays left or right, but if she actually gets to play, then she determines the payoffs for both players, left being a loss of 5.5 for player one, and right being a loss of 5 for player one. So basically, player one has a dominant strategy here of choosing out. And player two also turns out to have a dominant strategy, which is to choose right, because choosing right gives 10 with certainty, choosing left gives 5 with certainty if player one actually plays in. And of course, we don't really have to run this game. It's quite certain the player two will play right here, which is a dominant strategy. Almost in all cases, I would assume the player one will also play out here. So notice that playing out also minimizes the difference between the two players. So even other regarding preferences, if you want to be fair and so on, playing out is also better. So playing the equilibrium prediction of the dominant strategies here is almost certain to happen. Now, this is not what we ran, because this is almost a thought experiment that it's going to happen. So this is the normal form game of this game. What we actually ran is this game. And the only thing that changed here is here the payoff for player one if he chooses in and player two chooses left. In this case, player one gets 5 with probability 0.9 and loses 100 with probability 0.1 otherwise. Now, it should be noted that this gamble has the expected value of minus 5.5, so we haven't changed the expected value from the benign game before. So all else equal, basically, if people only care about the expected value, we should get also the player one plays out, player two chooses right, and that's it. However, if player one underweights rare events, so behaves as if the minus 100 loss gets less weight than it truly deserves, for example, instead of 10% chance, it gets 3 or 4% chance, then you can do the computations and see that it's actually, this gamble would have a positive expected value. So if minus 100 only gets a 3 or 4% chance, then this gamble has a positive expected value, and therefore choosing in might be justified as long as player two would choose against her dominant strategy and chooses left. And this is what we set out to look at, whether player one indeed behaves as if they underweight rare events, and whether player two understands that she needs to choose left in order to get player one to go in. And a few words about the experimental details. We ran this on mTurk via O-tree. We had 39 dads, pairs of participants after exclusions. We excluded participants who actually, that made very few choices, for example, because their computer got stuck or whatever, it was online. It was 60 rounds repeatedly, so each time it's completely independent of the previous rounds. Each time the players chose in this game on the right here. We let them have both description, so it was on screen the whole time. This game was on screen the whole time, and full feedback. So after each trial, after each round, they knew what they got and what they could have gotten had they selected differently. We incentivize it. We give them a bonus payment for one randomly selected round. So basically, there should be no wealth effect. And you can see here the mean bonus. And we give them a 10 seconds time limit in order to avoid get stuck on one screen, and then their partner will not be able to play. And we excluded participants that did not meet this deadline more than a few times. We also pre-registered our expectations, which were that player 1 will indeed underweight rare events, whereas player 2 will understand this and choose left more often than not. And here are the results. Let's start with player 1. So player 1, you can see that chose in here 63% of the time across rounds, across participants. The mean aggregate choice rates of in, which is against the equilibrium prediction, is 63%. And here you can see it over time. And you can see that starting around round 25, it's roughly at an asymptote. So it's not that people learn that they should avoid this bad gamble. They actually like to go in and play it more often than not. And let's look what happens with player 2. Player 2 also understands that she needs to play against her equilibrium prediction by playing left, although the dominant strategy would be to choose right. And the reason, and there's a hint for this here, you can see that 63% of the time players choose left, but there's a hint that initially only about half of the participants understands that they should choose left against their dominating strategy, and then it goes up to around 70%, and with some delay, it teaches players 1, their counterparts, to actually also go in, and then everyone's happy. Player 1, although he chooses a gamble with a negative expected value, minus 5.5, is happy because he underweights rare events, and player 2 also gets something. 5 minutes? Was that 5 minutes? Okay, sure. Now, one thing to note is this point here. So this is the very first decision that player 1 makes. Over 80% of participants actually choose against their equilibrium prediction. So they choose in. And this does not follow from underweighting of rare events, because as I said, underweighting of rare events, as we know it from individual decisions, relies on getting feedback concerning an experience concerning previous decisions, and this is the very first decision. So what's happening here? So we were worried maybe this whole pattern of 63% in is not about underweighting of rare events, maybe it's something else. So we had a survey asking, we just let people play this once, only player 1, we let them choose once this game, and we asked them, why did you do what you did? And here's a small sample of, well, a representative sample, I guess, of what people said. They said, I wanted to play. They said, I wanted a chance to win something. They said, I wanted a chance to get the highest amount possible, which in this case is +5. I wanted to and also I didn't want to ruin it for the other person. So the other person here gets -5 with certainty if player 1 plays out, and player 2 can get something if player 1 gets in. So going in would actually not ruin it for player 2. So we also ran game 2, in which we kept everything the same, except we replaced the gamble here from a bad gamble that gives good outcomes most of the time to a bad gamble that gives bad outcomes most of the time. Now this has an expected value of -4.5, this gamble. It's -10 with probability 0.95 or +100. And here, if people want a chance of the highest amount, which is +100, they just want to play, they would go in. They don't want to ruin it for the other guy, same thing, they will go in. But if they underweight rare events, if they behave as if the -10 is, the +100 is less likely than it truly is, then they should stay out. And here are the results for this one. Indeed, we see that only 32% of the choices were in. So this is actually the average choice was indeed the equilibrium prediction. but it is also consistent with underweighting of rare events. Players 2, by the way, they choose against, so they choose 42% of the time, which is left, which is against their equilibrium prediction. So most of the time they converge to the equilibrium prediction, but they seem to learn to choose more and more this dominated strategy, maybe to get players 1 to go in. Notice here that in the very first round, players 1 again go in more than around 80% of the time. So it's the same thing. I want to play. I don't want to ruin it for the other guy. The same process goes on, but after they start getting feedback, very quickly they converge around the equilibrium prediction. So I have 2 minutes, right? Okay, so let me go quickly over this game. So we also ran this game in which we tested whether players 2 underweight rare events. Here, player 1 can go out and then get 0. If he goes in, there's either a -5 or +5, so it's unclear what player 1 should do here. But player 2, if choosing right, would get -5 with certainty. If choosing left, would get +5 or 0.9, -100. So in equilibrium, this is, so according to expected value, this should not be chosen. Right should be chosen. This is a stochastically dominated option. Left is a stochastically dominated option. Therefore, player 2 should choose right. And by elimination, player 1 should choose in. And what we see is that players 2 choose left more often than not. So they choose their stochastically dominated option 60% of the time, and players 1 are roughly 50-50. And this is a small sample, so we'll have to run some more to get more robust estimates. Let me summarize, and then we'll go to questions. So it seems that people underweight rare events also in repeated 2-player games. And it should be noted this is quite, so both players here chose their dominated actions. Player 2 chose a strictly dominated action in game 1, and player 1 chose a stochastically dominated action, meaning that any risk-averse or risk-neutral utility maximizer should not choose to go in that game, but still most people chose to go in most of the time, and most players 2 chose their dominated action in order to get players 1 to go in. So other players may play their dominated actions to account for this bias. I will skip the why underweighting of rare events and go to questions, and if we have time, we'll go back to this. So that's it. Thanks.
Thank you. So now it's time for questions, if we have any. So if we don't have questions, or we have.
Yeah, maybe you said it's not about entertainment, right? So it's not that they just want to be entertained by the just playing the game and seeing what the result is, because yeah, it's more about like the framing of what the thing of the, if it's a positive or negative framing kind of for the participants, right?
So the positive, sorry, the last sentence again?
If it's like a positive, like more positive or negative framing for the participants, so they just believe that they have higher chances because the framing is kind of different.
So there's no framing. We just tell them, please, this is the game. You know that there's another player playing. You're either player 1 or player 2. And that's it. There's no framing going on. And if it was about entertainment, I mean, I want to see what happens. I want to see the choice of the gamble and so on. Then in this game as well, we should see that people go in, because this is the entertaining part. Seeing if I won, right? This is a lottery. There's something entertaining about this. Moreover, we show them what would have happened had they chosen differently. So if it's about, so it's a little bit more engaging. So. Beating the odds, so to speak. And so there is some kind of form of entertainment there, but this game would have to we'll also have to see people going in high numbers, and we don't see this.
Yeah, true. Thanks.
So can I ask now?
Sure.
So basically you have two observations here. One is a demonstration, which was your original goal, was the demonstration of the robustness of underweighting of error event in games. But then you have the really surprising result that in the first trial, this idea of, for some reason, you don't get a prospect theory, the decision prediction that we typically get in decision from description. How do you explain these findings? This is really, and it's really strong effect.
Yeah. So yeah, I agree. But so prospect theory is about individual decisions, and I'm not sure it would. Advocates of prospect theory would say, yeah, we have good predictions for what happens in two-person repeated games. Well, even two-person one-shot games. So we should
but
not,
you know, there is
sure.
people. But people apply prospect theory to explain behavior in the stock market, which is kind of a game.
So I agree. This is not the best model to use when social uncertainty is present, even in one shot. And more than that, I think it's a false model. It would be a very bad model. And indeed, we get the opposite prediction from prospect theory, so to say, because I'm not sure there is a prediction here. And people overuse prospect theory in a context that has social uncertainty. Definitely, I would not recommend it. It seems like there's something else going on. People want to play, people they have other regarding preferences and so on. And I would definitely, so this is another effect, but within the context of a game, of a lab game, I'm not sure that prospect theory would be something that people would advocate for. So I wouldn't make that much big of a deal of it.
Okay, thanks.
Okay, thank you. Thank you for the very interesting presentation. I think now it's me. Okay, so Ori, will you take time for me?
Sure.
Great.
I'll let you know 5 minutes before the end.
Yeah. Okay, so thanks all for staying till the last talk of this session. So I'm going to present the joint work on the value of alert systems and gentle rule enforcement in addressing pandemics. This is a joint work with Ori, whom you heard a few minutes ago, Edith, and Ido Erev. And unless you missed me, here is my photo. So I will start. So I think I don't have to tell you that COVID-19 brought a global crisis in the whole world. There are a lot of deaths and a lot of economical consequences. And the question is, how can we try to fight the pandemic? So maybe we can learn something from the Chinese success in fighting pandemics. If we look at the Chinese, where the pandemic actually started, we can see that actually now there are virtually no new COVID cases. This is from my checked yesterday. So basically they eliminated COVID at all. Unfortunately, this is not the case in Israel. We have about 3,000 new cases each day. So what the Chinese did, at least one of the things they did, they implemented a harsh rule enforcement. The harsh rule enforcement basically almost forced people to use tracking applications, and people could enter different places only if they showed a green code. Unless they had a green code, it was very difficult. It is very difficult for people in China to go to any places. So the question is, can the Western societies learn from the Chinese experience and from the Chinese success? And what is the challenge? The challenge is that implementing such a policy in Western democracies might be very tough because of the privacy issues, because of the issues of freedom of choice, etc. So we wanted to investigate it in the lab in a 4-person interaction game. Okay, So what are our experimental assumptions? The infection risk of the person, it depends on his own behavior, whatever he behaves recklessly or behaves responsibly. So whatever I wear a mask, whatever I keep whatever I keep a distance, it depends on this. And it also depends on the behavior of other people. So even if I behave very responsibly, but other people behave recklessly, it increased my risk of getting infected. Okay. Now, the reckless behavior is also beneficial most of the time. I think it's a logical assumption because wearing a mask, for example, is not that convenient. And most of the time when I wear a mask, when I don't wear a mask, it is just more convenient for me. So this is the better behavior most of the time. And if everyone behaves responsibly, the responsible behavior is better on average. This is our assumptions in the game. And here I will show you the experimental paradigm. So it's a 4-person interaction game, incentive-based, and it is a repeated choice, similar to the one you saw before. So here is the basic setting of the game. The participants had to choose between these two buttons, A and B, and they had a full description of the payoffs. So if they choose A and all the 3 other people also choose A, they will receive 0 points for sure. But there is a risk. If at least one of them behaves recklessly and choose B, then there is a small chance of getting infected even if you behave responsibly. And if you choose B, most of the time you win 1 point, but in rare occasions you lose 60 points. So again, here is the basic game setting. And here the participants had to choose one of the 2 alternatives. That assumes that they made the choice of the alternative A. So now they see the feedback screen. So in this trial, you choose A, your payoff is 0 points. Had you selected B, you would have gotten 1 point. Again, they see the game payoff screen. It's always on the screen. And now they have to move to the next trial. So they have to click on the next button. They click on the next button and they proceed to the next trial. So let's assume in this trial, I decided to choose alternative B. So I click on it. I receive 1 point. I see that I chose alternative B. Your payoff is 1 point. Had you selected A, you would have gotten 0 points. Again, I have to, and again, I see the game payoff. Again, I have to click on the next button to proceed to the next trial. So as you can see, unknowingly to the participants, A represents the responsible behavior, which mostly gives 0, and for sure 0 if all the persons choose A. And B represents the reckless behavior, which mostly gives a positive payoff, but has a small probability of getting infected. And also this game has 2 Nash equilibria. One is the efficient one, when everyone chooses A and everyone gets 0. And one is the inefficient one, when people choose to behave recklessly. Do you have any questions about the game setting, the basic game setting? Okay, so I will proceed. So what interests us is what is the B, the reckless choice rate. Okay, and in this 4-person game, the reckless choice rate, unfortunately, was 91%. So maybe it does not surprise you too much after you heard Ori's talk, because people presumably underweight the -60 payoff. Most of the times they get +1, so they choose the reckless behavior. As you can see, it's not driven by a few groups. Here you can see the individual behavior within group. Here I present the first 10 groups, and each line here present the behavior of one individual, and the bolded line present the mean of the respected group, and here of all groups, and it's in the 5 blocks of 12 trials. So as you can see, most of the basically all groups converge to the inefficient equilibria where people choose the reckless behavior. Okay, and this behavior is predicted both by the cognitive hierarchy model and two variants of the naive sampler model. I will talk about the naive sampler model later. The cognitive hierarchy model, basically it assumes it's a level K reasoning model. It assumes that the level 0 participants behave randomly and level 1 participants play best reply to level before them. So level 1 plays best reply to random choice, and level 2 plays best response to level 1, etc., etc. So as you can see, all models predict the high reckless rate in this setting. So this is basically the situation that happened without any intervention. Without intervention, there will be a high infectious rate because a lot of people choose the reckless behavior. So now we look how can we increase the responsible rate. And going back to the Chinese example from the beginning, as I said, they use a tracking application to reduce their reckless rate. So we compare two types of interventions. So intervention number 1, it eliminates the social externality. So as I said, in our basic setting, even if I behave responsibly, choose A, I still have a chance of getting sick if other people behave recklessly. So this intervention eliminates the social externality. It's a protecting app. It eliminates it. So if I behave responsibly, I'm for sure protected. I will get the 0 for sure, regardless of the behavior of other participants. So basically, this is the game that I see. And all the many theories like loss aversion, risk aversion, and cognitive hierarchy model, they predict that this intervention will be very successful in increasing the responsible rate. So this is what we test now. And the question is, what will be the reckless rate in this setting? So basically you have a choice between 0 for sure and 1 with probability 98 and minus 60 otherwise. And again, based on Ori's previous talk, now you can guess that because people underweight the rare events, this application was not that effective. Indeed, it was not effective at all. So there is a 92% reckless rate. And here you again see the group behavior. So as you can see, all the groups converged to very high reckless rate. It is against the prediction of cognitive hierarchy model, but it is the prediction of the naive sampler model. As I said, I will talk about it in a few minutes. Okay. The second intervention that we investigated is a gentle rule enforcement intervention. It's an enforcement app. And the potential of gentle rule enforcement was previously shown by Erev and his colleagues. And the idea is that basically you have to implement a high probability, low magnitude punishment instead of low probability, high punishments. We implement a very low punishment, but with very high probability. Okay. So what we do here in this setting, basically, if you behave recklessly, we punish you with 1.2 points loss in this setting for sure. So the game becomes A is the 0 for sure. And if you choose B, you for sure lose 0.2 points with probability 98 and 61.2 otherwise. And as I said, this is a gentle punishment of the reckless behavior with very high probability, 1 in the current setting. And the question is, what is the reckless rate, the B choice rate in this setting? And the results are that it's a 15% reckless rate. So as you can see, the second intervention was very effective in reducing the reckless rate. All the groups, I present only the first 10 groups. We actually had a bit more. We had about 13 groups, I think. All the groups converged towards a good equilibrium. So most of the participants choose the beneficial behavior, the responsible behavior in this setting. And here it is as predicted both by the cognitive hierarchy model and the naive and the varieties of the naive sampler models. So now I want to talk in a few minutes about what is a reliance on small sample model. So let's take the example of the basic setting in which you have the choice between A and B. Notice that all the games are a mix of, as in the previous talk of Ori, a mix of description, because you have the description all the time on your screen, and experience, because you learn from your behavior, and it's third-person games. So let's assume that in this game, in the first 36 trials, this is the payoffs that you saw on the screen. So if you choose in the first trial, A, you saw 0, and B, you saw 1, etc., etc. And now you're at trial 47 and may have to you have to decide what should you choose in this trial. So a reliance on small sample model predicts the following. It says that you randomly recall a certain number of certain number of your past experiences. So let's assume that you thank you. So that you recall a sample of 3. So, and let's assume that you randomly recall trials 2, 5, and 46. Okay, so this is the trials that you recalled. So now you just calculate what worked best in your small recalled sample of experiences. So the outcome of A in your recalled sample was 0 plus 0 plus 0, a mean of 0. And in your recalled sample, the outcome of B were 1 plus 1 plus 1, which is 3, a mean pay of 1. So if you base your decision on a small sample of your past experiences, in trial 47, you will choose to behave recklessly. You will choose the alternative B. By the way, notice that the reliance on small sample, it also implies the underweighting of rare events. Why it implies the underweighting of rare events? Because the rare events happen very rarely, because it's rare. And if you recall only a small sample, there is a big chance that in your recalled sample, the rare event will not be recalled. And thus, you will behave as if you underweight the rare event, which is the getting infected in this case and getting the minus 60. And to conclude, we examined 2 possible app interventions to fight pandemic. One is the protecting app that eliminated the social externalities. And the one is the gentle rule enforcement app. And our analysis suggests that there is a major advantage of the gentle rule enforcement app. I want to add one more thing. I really think that this pandemic shows us that people, even if at the beginning, from the description, many of us were afraid of the pandemic, we start to behave as if it will not happen to me. So many of us start to behave as if we underweight rare events and the rare risk of being infected. And this simple, the reliance on small sample provides an explanation why we behave in this way. I think this is the end of my story. So now it's time for questions, if we have such.
I would have one. So could you check what they recall, like what the participants recall? If you like, you could ask them, yeah, what results would they recall from their last rounds that they played? So you kind of, yeah, could check, yeah, your hypothesis that they really do not have in mind these rare occasions, because yeah, I would also think, okay, it really hurts to lose these 60 points, so maybe I would still remember.
Thank you. Obviously, we could do it. We have not done it. We have not asked them what they recalled, but Ori and Dido with Kinneret, they wrote a few years ago a very nice paper on the recency effect, wave recency effect, sorry. So what they found that after a big rare loss, actually people behave as if in the upcoming trial, the big loss will not happen again. They behave like a wavy recency, like they after 3 or 4 trials after the big loss, they start to behave as if they're afraid again of the big loss. And Ori, please correct me if I'm saying something not correctly about
Yeah,
it.
so actually they underweight the rare events most 3 trials after it happens, and then they start underweighting it less and less and less, and they behave, the maximal sensitivity to the big loss, for example, would be around 15 rounds after it happened.
And also notice that in this paradigm, they have the full description all the time on the screen and full feedback. So actually, we believe that if you don't show the description, the results will be even stronger, because if you believe in silence or whatever, or description, you see the -60 on the screen, you see that you can lose a lot of points. So if you don't see it, we believe that the results will be even more extreme in the direction of underweighting the rare events.
All right, thanks.
Thank you.